Well, Greenland wasn't named Greenland because it was white. It was named Greenland because the margins of it were green when the Vikings colonized it.
One unfortunate thing about our thermometer record is it basically starts at the coldest part of the Little Ice Age, back in the mid-19th century, about 150 years ago. And so if our temperature record starts at the coldest period we've seen in probably 10,000 years and is warming up out of that, you would expect that the most recent periods should be the warmest, naturally.
Temperature goes up, and temperature goes down. It's hardly ever standing still, at least not at the level of tenths of a degree, which we're talking about. And every time it's going one way or the other, society has responded by saying it's going to continue going. Every time it's turned around. So we had warming concerns in the late 30s, when for many areas of the world, including the Arctic, it warmed more than it did today. Then we had mild cooling from the 40s to the 70s, which, incidentally, when you looked at the published records, looked much more profound then than it does in the records we're shown today. But nevertheless, then we had global cooling, and there was all sorts of hysteria in Time and Newsweek about man's emissions were going to give rise to so-called aerosols, and they were going to cool the Earth, and we'd go into an ice age. And then that turned around, and we had warming. And now we have had for 20 years, actually more, 25 years, am I wrong? Yeah, something like that, 20 years at least. Declarations that if we don't act now, the end of the world is nigh. You know, I'm sure people are tiring of this after 20 years.
People should understand that the climate system always changes. The temperature of the planet is always rising or falling. Glaciers are always expanding or retracting. And think about this. If you had a choice between receding glaciers and advancing glaciers, you would want receding glaciers because nobody wins when there's advancing glaciers. Just like the global temperature, sea level is either rising or falling. There is no set standard for sea level. The sea level is rising right now, as it has for the last 15,000 years, because ice that's on land is melting. Since the last ice age, it is melting. There is more ice to melt, just as it happened 130,000 years ago when the sea level was 20 feet higher. We can expect that much more water to melt. But we have pretty good measurements of how fast that's happening. And right now, that's happening at about 1 inch per decade. 1 inch per decade is how the sea level is changing. Now, that's been going on for many, many decades. And you cannot attribute that to human effects.
It's not a hard calculation to double CO2 and see what it does to global mean temperature if you hold everything else fixed. It gives you about 1 degree centigrade, which is not a big deal. I mean, some people argue a tenth of a degree is a big deal, but that's nonsense. Models, on the other hand, commonly give you 3-4 degrees. What's happening in those models, and I'm saying in the models, not nature, is the main greenhouse substances, water vapor and clouds, are behaving so as to take anything man does and make it much worse. But there is a problem with that picture, apart from the fact that I think it's untrue, and our own studies are showing that. But the problem is, and this is what people don't realize, I'm talking about doubling carbon dioxide, but the important thing for climate is how much it imbalanced the radiative transfer. If we ask how much in the way of CO2 and methane has been added to the atmosphere in the last century, and what percentage of the greenhouse perturbation is compared to doubling CO2, it's 3/4. In other words, in terms of greenhouse effect, we're 3/4 of the way to a doubling already. And our alarm is based on models that are saying we should see, for a doubling, 3-4 degrees. The most conservative, 2.5. And we've seen a half. And we can't even say that's due to men.
Yes, I think that any politician today would be wise to be very careful about what they say about environment, because you are immediately branded as being on the far right, as being, a destroyer of worlds, if you side with industry these days. I mean, industry has become a dirty word. Now, I grew up in an industry. I always thought being industrious was a positive thing. But it no longer is, apparently. Apparently, industriousness is what is destroying the world. And industry, i.e. capitalism, is the main culprit in the piece. When in fact, that seems to me that industry is what is feeding and clothing and housing us every day. And I don't see an alternative institutional framework being offered up.
You got to be rational in your evaluation of the data. And I feel that a lot of these people just think that as a species, we got too many Hummers on the road. We're, too many air-conditioned big box houses, and we're consuming, and I feel that way too. But I don't feel that we can blame climate impact or climate change on us. Because of that, it's wrong. Maybe we have too many Hummers on the road, but that's a different issue.
A lot of activists behave as though those are mutually exclusive, that like automatically the more people there are and the more stuff they use, the more damage will be done to the environment. But that's not true. It's a terrible myth, actually, that's been created. And Paul Ehrlich is part of the reason why that myth exists, because he has pushed all along the idea that every American is the equivalent of 80 Bangladeshis in terms of the amount of damage that's done, because they consume 80 times as much material energy. But if you actually look at Bangladesh and the United States, that doesn't translate. There's no way that every American is causing 80 times as much destruction to the environment as every Bangladeshi person. As a matter of fact, poverty causes more damage to the environment in many cases than wealth does. If you actually look at the environmental impacts of poor people living in Guatemala, living in Bangladesh, living in Kenya, you can see it with your eyes. The environments there are not in such great shape because you have people trying to eke out a living who don't care about tomorrow, haven't got the money to clean the water after they foul it, haven't got the money to replant the forests after they cut them for fuel wood. Whereas if they did have sufficient wealth to be able to think beyond the next day or the next week, they would start to care about those things just like we do. So that to me is the big division today in environmental thinking, is right at the very root of it, thinking that human beings are actually a cancer in the first place, so who cares about them? And then at the same time kind of romanticizing the hundreds of millions, billions of people who are living in a state that we would not consider to be dignified. They don't have basic sanitation and clean water and health care and education. Now that is not a dignified life. I have never heard any of these people recognize that poverty is actually an environmental problem. They seem to think that poverty is the solution to our environmental problems. That if everybody lived in poverty with very little, that then the earth would be fine.
The most common failing I find is in the selective use of evidence. People, perhaps naturally, tend to reject evidence that contradicts their favorite theory or hypothesis. That's quite common. It's now been institutionalized in the following sense. Take the IPCC, for example, the UN panel on climate change. They write fairly decent reports. The reports typically are 800 to 1,000 pages. without index. Nobody can read them, really, unless you, like myself, unless you're one of the reviewers and you have read through the report. And then a small group of government scientists gets together and writes a summary for policymakers. The ones that I've seen are very selective. They reject evidence that would cast any doubt on human causes of global warming. And naturally then they come up with statements like, there's evidence for human causes of global warming. They have to be careful because the report itself doesn't say that. But you can word the summary in such a way as to suggest that the preponderance of evidence or the balance of evidence suggests human causes. And that's what they do. I have long argued that instead of a summary for policymakers, we need a policy for summary makers.
Oftentimes, the summaries are much more strident and definitive than the following text. I think that's quite clear in the third assessment report. But there's also some very strange things that happen in the making of the overall reports. In the one that's on the table right now, in early draft, there was a wonderful illustration showing all the, it's like a table with lines on it that showed all the places around the Earth for the last 11,000 years where it had been warmer than it was prior to the Industrial Revolution, somewhere back between now and 11,000 years ago. And right up on the top, near the north end of this thing, was a big streak that indicated about 4 degrees Fahrenheit warmer for Siberia and North Russia and North Eurasia from about 3,500 years ago to 11,000 years ago. 7,000 years plus where it was warmer. And it had the reference in the scientific literature where it came from, MacDonald et al., from the geography department at UCLA. When the next draft came around, it was missing. It was gone. Everybody knows this guy's work. We called him up. Hey, did somebody refute your work on the tree line? No. Why did it disappear? I haven't a clue. The IPCC is not peer-reviewed in the strict sense because in the IPCC, the people that write the thing get to decide what reviews they want to listen to. In other words, if they don't like what somebody said, we don't necessarily have to pay attention to that.
The scientific debate in this area is almost non-existent because the people who have another point of view than the official one find it very difficult to make themselves heard. They speak to one another, they encourage one another, buy each other drinks, but in terms of registering with their fellow scientists, never mind the general public or governments, they've had a very, very hard time of it. A friend of mine who made a television program which cast doubt on the global warming story was told by a government official that he would make sure that this producer never made a program again.
I suppose in the world, and I've been around the world, it is something I've found that people tend to believe what they want to believe. And I found that scientists are people. And it turns out that scientists, and I don't exclude myself from this crowd, will color what they see and slant how they view things to fit with an assertion they want to be true so badly, they will avoid looking at anything that is contradictory. In that sense, it becomes a religion, because a religion is based upon things really that you cannot test. They're based upon faith.
Obviously, someone who says global warming is not as important as it's made out to be is going to be under some pressure, considerable pressure, from his peers, many of whom depend on the global warming scare for their livelihood.
The global warming lobby is a political movement. Newspapers are there to print exciting stories. The global warmers claim every extreme is caused by global warming. So news people naturally look around for extremes and report them, and then just say it's because of global warming. Now, a lot of the scientists involved in global warming theory might not actually agree that there's any evidence that more CO2 equals less fish, but they won't speak out when nonsense is said in their names, because they are funded by a climate crisis industry.
I saw Mr. Gore's film. I've actually read the book as well. There's an animation of little mosquitoes moving up a mountain. What Mr. Gore says, to begin with, is that Nairobi was founded in a place that was not malarious because it was too high. That's simply not true. Nairobi was a point on the railway line that was being built from Mombasa to Kampala, right on the edge of the Rift Valley. They decided to put a station here before they started the difficult engineering of descending into the valley. And it was malarious. There was malaria there right at the beginning. In the period between the First World War and the 1950s, when DDT began to be used, there were 10 major epidemics of malaria in Nairobi and to higher altitudes, to Londiani and Eldoret. Nairobi is about 1,600 meters. Eldoret is around, I think it's just over 2,000 meters. There was transmission of malaria up to about 2,500 meters. So it's complete nonsense to say that malaria has moved up to Nairobi. In fact, if you look at the data for Nairobi, you'll see that in recent decades, it's been declining. This is the kind of misinformation that has been fed to the public continuously on malaria, on West Nile virus, and all these other things.
It's curious that there has been great reluctance by the, shall we call it, the global warming community of scientists to accept anything but greenhouse gases as the cause of climate change. To use the colorful language of former Vice President Al Gore, I would call them deniers. They deny that the sun can have an effect on the climate, or that solar variability is the main cause of climate change.
After the first big report in 1990, which everybody seemed to believe about global warming due to carbon dioxide, I continued as an independent and I hope objective reporter to look at other causes of climate change. And as I knew from writing about the subject for many years, the sun had until that time been regarded as the chief candidate. And I was actually invited to script a TV series to be sponsored by the European Space Agency about the sun, because they've got several solar missions coming up. And the Director of Science of the European Space Agency said, and of course I would deal, wouldn't I, with the sun's role in climate change. So I was kind of briefed to pursue this subject. I should mention that although the European Space Agency had promised half the money for this little series, they could not find a single broadcaster who would take it because it wasn't politically correct.
Kyoto, the general agreement is, at whatever expense, does nothing. And so it's telling people, you know, changing a light bulb will save the world. That's I guess, a high for some people. But it's nonsense. And so one might reasonably ask the environmental movement or the scientists, what exactly would be needed if we're already 3/4 of the way to a doubling of CO2 in terms of the greenhouse effect, and we think that is horribly dangerous, And there's nothing we can do about that anymore, but we don't want it to get worse. I figure it would involve rolling back emissions not to 1990, not to 1995, but maybe 1840. And that's a pretty extreme thing for a speculative hypothesis that so far is not in agreement with the data.
There are no doubt going to be some positive effects if the climate continues to get warmer. I mean, a large portion of the Earth's surface is like an ice box where people can't really live in any numbers. You know, I ask people, where's the most people, Barrow, Alaska, or Sao Paulo, Brazil? You know, there's hardly anybody living in all the Arctic regions of the Northern Hemisphere, which encompasses all of Siberia, all of northern Canada and Alaska, and part of northern Europe. I mean, it's a huge area of land in which it really isn't possible for many species to make a decent living. It's pretty sparse. And so when I look back in climate history and realize that actually we're now in a cold period, even during this interglacial, this is still a relatively cold period compared to much of the history of life on Earth over the last 4 billion years. There's been long periods of tens and even hundreds of millions of years when it was much warmer than it is now, and life flourished. There was no ice at either pole. All of the land surface was basically tropical or subtropical. The great Carboniferous forests that covered most of the land for millions and millions of years, well, life flourished. And actually, one of the main restrictions to life on Earth is called frost. If you look at the areas on Earth that get a hard frost, you see a huge reduction in species diversity in that part of the world. Whereas in the tropics and subtropics, that's where most of the biodiversity is on this planet because it doesn't have frost. Frost kills, like 90% of all the species in the world cannot live with frost. So I think that perspective is completely missing from the discussion today.
What we're doing is going hysterical over a few tenths of a degree warming in a very noisy record, where the warming is not indisputable, as they say, but probable, and models that are getting the answer wrong by 300%, assuming some mysterious factor has canceled the difference, but will quickly drop out of the picture so that catastrophe will be upon you. It's going to look silly for the future. We're really contemplating our climatic navel in looking at tenths of a degree. I mean, if somebody was worried about their body temperature to 100th of a degree, you'd regard them as a nut. For the last 100 years, it's like getting excited because you've thrown a coin and gotten 2 heads in a row. No, I mean, in the larger scheme of things, we've had 2 kilometers of ice on our head, 20,000 years ago. And then we've had warmer periods 5,000 years ago. We've had the medieval optimum, 1,000 years ago. We've had the Little Ice Age. I mean, change is the norm for the Earth. I mean, not change in the sense that it turns from 1,000 degrees to 10. But change, has been in the level between 250 and 300 degree type thing, within a 20, 30 degree range. That happens all the time.
The sun affects us directly, of course, when it sends down its heat. But we now know the sun also affects us indirectly through clouds. Clouds have a powerful cooling effect, but how are they formed? In the early 20th century, scientists discovered that the Earth was constantly being bombarded by subatomic particles. These particles, which they called cosmic rays, originated, it was believed, from exploding supernovae far beyond our solar system. When the particles coming down meet water vapor rising up from the sea, they form water droplets and make clouds. But when the sun is more active and the solar wind is strong, fewer particles get through and fewer clouds are formed. Just how powerful this effect was became clear only recently, when an astrophysicist, Professor Neir Shaviv, decided to compare his own record of cloud-forming cosmic rays with the temperature record created by a geologist, Professor Jan Weitzer, going back 600 million years. What they found was that when cosmic rays went up, the temperature went down. When cosmic rays went down, the temperature went up. Clouds and the Earth's climate were very closely linked. To see how close, you just flip the lines.
We just compared the graphs, just put them one upon the other, and it was just amazing. Jan Weitzer looked at me and says, you know, we have very explosive data here.
I've never seen such vastly different records coming together so beautifully to show really what was happening over that long period of time.
The climate was controlled by the clouds. The clouds were controlled by cosmic rays. And the cosmic rays were controlled by the sun. It all came down to the sun.
Okay, so what I'm going to do for you in the next few minutes is describe a summary of the research that my group has carried out during the last 6 years or so. And what I'm going to be emphasizing is research carried out on a place called Effingham Inlet on the west coast of Vancouver Island, and several fjords that are further up the coast of British Columbia. Now this looks like a small area, but this is probably about the size of Western Europe right here. So this covers a very wide geographic region. And we'll be looking at places that are in two very different oceanographic regimes. Effingham Inlet is in an upwelling zone around here where waters are being influencing this area from the open ocean, whereas these areas up here are more restricted and it's more influenced by continental type processes. So here is the fjord opening. There are a couple of basins that are found here, and these are what are of interest to us. And the reason for that is that, this is the open ocean, is that there are sills. And these sills block the flow of water coming from the open ocean and resulting in these inner basins having little oxygen circulation down to the bottom of them. So the water flow comes in like this, and then it becomes stagnant at the bottom. In this outer basin, conditions are dysoxic. That means that there's very little oxygen. But on the inner basin, there's no oxygen whatsoever. And that is really nice for us, because what that means is it records sediment undisturbed by any animals crawling around on the bottom. So basically, year by year, we have a very, very continuous record for several thousand years. This is another shot, but this is further north now. This is the Seymour Blees Inlet Complex on the mainland coast of British Columbia, and we're looking at several fjords that stretch, several, maybe 30 kilometers inland, and they are very restricted. There's something here called the Nakwatko Rapids, which basically block the main circulation of water coming in from the ocean. So it's very difficult for all the water to exchange on the turn of a tide. And as a result, it becomes anoxic in here as well, but for very, very different reasons than we see before. And this is just a shot, again, superficially, looks very similar to what we saw in Effingham Inlet, but oceanographically very different. And these are shots of some of the equipment that we use as we take our cores. Now, everything in the Northeast Pacific, all the way from California on up into Alaska, is controlled by two weather systems. Okay, the Aleutian Low dominates this region in the wintertime, and it results in very rainy conditions. And when it's raining in those narrow fjords, that results in a lot of sediment being sloughed off into the basin and forms layers. So this is what happens in the winter. In the summertime, we end up with sunnier, drier conditions. But what happens then is, because the way that this weather system it has a gyre which goes in a clockwise fashion, it results in upwelling. And so it's warm and dry, so there's no sediment washing into the fjords, but we end up with all this nice minerals are being brought up from the deep ocean, and that allows the phytoplankton to grow, and we end up with very thick layers of things like diatoms and various other microfossils that we can look at in our record. So those are the two dominant controls over climate. So here's another shot showing some of the large cores. This is very expensive research. These ships cost $25,000 a day with a large crew. These cores here are very heavy, weigh several tons. If you do not handle it correctly, somebody could become hurt or lose a finger or something like that, which happens periodically. So here's a core about to be dropped into the ocean. The sediment is very mucky, this stuff. So at the very surface of it, these cores are so heavy, they sometimes overshoot and go deeper into the sediment. So to get the very top of the sediment, we use something called a freeze core. And what this does is drops down to the sediment, and it's filled with dry ice. The dry ice results after about 20 minutes, all the sediment around it being frozen to it, and then you extract it, and we end up with a perfect record. And here's a little bit of mud frozen to the side of that. So we get this record right up to last week, basically, when we're collecting these sediments. And here's what you end up with. Here's what this mud looks like, and it's basically about 5,000 years of mud. There's not enough time here for this stuff to turn to rock or anything, so we're just looking at soft mud that has layers in it, and here's what we see. And I mentioned that what we see is everything here is controlled by the North Pacific High and the Aleutian Low. And so in the wintertime, when this region is much rainier, we have the Aleutian Low dominating, and we have a lot more grains being washed into the inlet, and we end up with these darker layers. And you can see, looking up through this, that no 2 years alike. Look at this. This tells us that this was a rainier time. And I mentioned the North Pacific highs when we had upwelling, and the phytoplankton loved that. Look at these thick layers right here. These are years where the diatoms loved it, and so they had thick layers being laid down. Over time, things change. The North Pacific High may dominate for a few years in a particular orientation. The Aleutian Low may do it for a few more years, and it forms these cycles and trends. And we scan this with a computer, and the computer can look at the thickness of the layers and can look at the changes in the darkness of the layers. And the cycles and trends that the computer can recognize, we call it a time series analysis, allows us to see, is climate cyclic? Does it have any particular trends? And that's really important because, for example, this Northeast Pacific region has only been inhabited by Europeans with thermometers since really well into the 19th century. We have no record much. And so it's very important if we want to understand climate, which often is varying on cycles longer than our lifespan, we need to look at these very complete records. And the record that we have in this region extends back at least 5,000 years, and it's at this sort of resolution, so it's unprecedented. This is one of the highest quality climate records that are available anywhere. Now the first little core I'll show you is a freeze core. I showed you one of these ones. This was taken from Effingham Inlet. And this is where the core was taken from this anoxic basin in here, anoxic with no oxygen in it. So there was no oxygen down at the bottom waters right here. The bottom of the core bottomed out in an earthquake record. There was a slump in 1946. There was a major earthquake in this area. And it ended in 1993. We didn't get right up to the top because as we pulled the freeze core up, it had to come up through 200 meters of water and it washed some material away. But we went year by year by year by year by year, counting all the diatoms. We dated it so we know all the different things that were going on around here. So we did something called time series analysis. As I mentioned, that the computers that we have scan the X-rays right here and recognize changes in the thickness of the layers and their grayscale. So the variations are found. And when we did this, we did something, I love this, wavelet analysis right here. This is a type of time series analysis which allows you to recognize trends visually in something. And so what we see here, all these little blobby bits up here is the annual layers. Every year a layer, so it can recognize that. It also recognized in here, at this level right here, that occasionally an El Nino impacts the area. The Northeast Pacific, if there's a big El Nino, has a major influence upon climate. We're a little further north. It doesn't always happen. So once in a while, we have some El Ninos. But the big thing that was happening throughout this entire record was a 10 to 12-year cycle that was dominant throughout. And we picked up the same thing when we did a different type of time series analysis called spectral analysis. We recognized an 11-year cycle in the grain size that are washed in the wintertime and also with the diatoms. And so they had the same 11-year cycle. So this was cool. We said, what's causing this 11-year cycle? Then we went and looked at those long piston cores, the ones that were taken with these great big cores that weighed several tons that are lower down to the ocean bottom. And this record here extends from about 2,000 years ago or 1,800 years ago back to nearly 5,000 years ago. And what we saw when we did the same sort of wavelet analysis in here was that we had all these solar cycles. The 11-year cycle is called a Schwabe cycle, but piggybacking on top of that are longer solar cycle. Here's one's called the Gleisberg cycle, which is 75 to 90 years, something called a Seuss cycle, and then a very long cycle called a Bond cycle. And these showed up here quite clearly through here. And we also, so here's the Gleisberg cycles right here, and here is the Seuss cycle, and there was a major oceanographic cut here. So I'll describe that. And here it shows it more clearly. And what I'm emphasizing here are the Gleisberg cycles, because to discuss everything would take a long time. So here's a Gleisberg cycle blipping in. This is a solar cycle which is 75 to 90 years. Here's another one. Here's another one and another one. So they gain strength, they fade out, they gain strength, they fade out. Here is the Seuss cycles. This major cut right here, 3,500 years ago, this marked a neoglaciation. There was renewed glaciation in this entire region about 3,500 years ago, which we pick up in the oceanographic record as well. So something major was going on oceanographically as well as in the ocean. The major funding for this research on the West Coast was initially from the Natural Sciences and Engineering Research Council of Canada. And the main reason I got this money was that there was problems on the West Coast. They had these major fisheries going on with various species that they go on quite nicely, then all of a sudden they crash. There'll be a major fishery one year and there'll be none the next. Problem is, their fishery records are very short. They only reach back into the early 20th century in many cases. And so the fisheries managers were very, very interested in understanding, are there cycles and trends in fishing? And so we were mandated to look at these cores to see if we could find any records of fish remains to see if they would tell something about, are there actually cycles in here? The two important commercial species we looked at were northern anchovy and also Pacific herring. Okay, and they have been found to undergo significant population changes through time in this region, and as a result, they were a good target for us. Now, again, because of the brief fishing records which existed for these important species, it's really important for us to go back and try and see whether they change over time, because there are huge fleets. There's thousands of people employed in these fisheries, and their success of them, they want to know, are they going to crash? What drives it? We had the same problem on the West Coast with salmon fisheries, and that they don't understand those very well as well. One year they'll have a huge population comes out of nowhere, and the next year it'll be nearly gone. They blame it on overfishing, they blame it on oceanographic changes, but no one really knows for sure. So in order to understand these things, you need to look at the longer record. Well, here's Pacific herring, and this is what we look at. This is a nice drawing of a Pacific herring. This is what a modern scale looks like, and when we look in these little sediment layers, we pick them apart, you can find fossil scales. And I have students that count these things, and they look at changes over time. Sometimes in the core there'll be almost none, other times they'll be very abundant, and we can employ statistical methods to try and figure out how they exist. Now, it's a cool water species, and in Effingham Inlet, it was very near its southern limit. So that's a great place to be, so if you're on the margin. And it likes conditions when annual water temperatures are above average. And so if you find warmer waters around there, you'll tend to find more of these things. So that's what controls Pacific herring. Northern anchovy, and this is a picture of its scale, and even to a person, a lay person, I think you can see there are very distinct differences in these scales. And so it's a very easy tool to try and count the relative abundance of these things. Now, it's at the northern end of its range in Effingham Inlet, and it likes it during enhanced upwelling. So lots of upwelling around, you find lots of these things. And as you saw just on that little graph, or on the X-ray of the core, that the conditions vary considerably in Effingham Inlet, and they'll vary considerably at longer scales as well. And this is what we wanted to look at. And this is what we saw, is that just as I showed you with the diatom and the sediment records a few minutes ago, the anchovy and the herring are fading in and fading out over time. And so that they have these long records. So here's the Gleisberg cycle. You can see them fading in and fading out. Here's the Seuss cycle right here. And they both underwent this major cut 3,500 years ago, and they continue to go on at the present time. Now, right now, we've finished off an anchovy regime right now. We're ready to have some herring seemingly start to come back again. But you can see enormous abundances of these things at time fading in and fading out in response to what seems to be solar cycles. So here we are at higher trophic organisms that are feeding basically well up the food chain, also responding to the same drivers which seem to be controlling the diatoms and the sediments that we saw. As we were began to develop some hypotheses as what might be controlling the patterns we were seeing, we saw all these solar cycles, what was a eureka moment for us was when we began to uncover, or we began to read literature which pointed out how climate amplifiers are influencing the solar cycle. And it's interesting, there are literally hundreds and hundreds of papers that have been carried out which have found apparent links between solar cycles and climate, which was quite heartening to us. The problem was, and here's an example right here, here's sunspots number right here, and this looks at global mean sea surface temperature, so they match up quite nicely. Here's another record right here, for example. This shows the surface temperature over time. This is looking at changes in solar radiation, and this little dotty line right here is the actual thermometer record. They match up very closely as well. We also found solar cycles as well in other records from our region. This is one right here looking at tree ring widths in the Kola Peninsula, which is up in northern Russia, and they found the same Gleisberg cycle we see, this Hale cycle, which is a 22-year solar cycle, and our 11-year cycle. So they were very clear, and this is all across the high Arctic, and there are many, many other records as well, right around where we were doing our research. So let's stop then and pause and talk about just what a solar cycle is and how it might correlate with the records that we see. This is a graphical image showing a transition between solar cycle 23 and solar cycle 24. Here we are right now just at the end of solar cycle 23, ready to start 24. And what happens is the sun across an 11-year sunspot cycle changes the intensity of the energy it produces very slightly. Here's at a solar minimum in 1996. There's hardly any sunspots. And then here's a solar maximum right here. Here's one from 1999. You can see these little sunspots here. Now, when there's an increase in sunspots, there's a slight increase in the amount of energy which the sun produces. And it throws that energy out into the solar system and strikes the Earth. And here it is right here. This is the energy change across this is from 1978, 88, up to 1998. Here's the peak. Here's a trough right here. The sun's output varies by about 0.1%, or 1.4 watts per square meter across an 11-year sunspot cycle. Problem is, and this is the problem that has been with all these research papers, the hundreds of them literally, through the years that saw this correlation between the sunspot cycle and apparent sea surface temperatures and between global temperature anomaly and so on, is that that's really not much energy. 1.4 watts per square meter across a sunspot cycle will not drive the climate change that we see. If you're going to have climate change, you have to have some kind of amplifier. And this is where everybody has been stymied for years, until very, very recently. Now, this is a nice graph right here which basically shows the solar wind. And that solar wind is coming from our sun, and the solar wind slightly varies a little bit across a sunspot cycle. As you move to the peak of a sunspot cycle, there's more energy being released, and that enhances the solar wind. Now, counteracting that, our solar system is continually being bombarded by cosmic rays. Cosmic rays are stripped down neutrons, which basically come from supernova within the galaxy. So these are basically continually bombarding our solar system. And and again, they're trying to get to the inner part, but they're being deflected by the solar wind. During a peak of a sunspot cycle, more cosmic rays are deflected, but some still get through. So when you have a trough in a sunspot cycle, more of these cosmic rays get through to the solar system, and when you have a peak of a sunspot cycle, the solar wind is stronger and more are deflected. And the question then arises, so what? What does that have to do with phytoplankton production in the Northeast Pacific? What does it have to do with Pacific herring or anchovy, or the amount of rainfall which creates the dark layers that we see, and so on? So let's look at another part of the equation. Clouds are important controls over climate in our planet. Okay, so cloud basically has two effects. Clouds can either result in greenhouse gas, or basically they can act as a blanket which makes the planet warmer, or they can reflect solar energy back out away from our planet and result in a cooling. Now, the result is that our overall planet, when you have more clouds, there's a cooling going on. So the more clouds, despite there be some result in a warming, some result in cooling, the overall effect is when you have more clouds, you end up with a cooling of the planet. And so the question then is, so what? Again, what do clouds have to do with my anchovies and my phytoplankton? What does it have to do with cosmic ray flux and so on? Well, here is the so what. Here's an interesting correlation that has been measured between low cloud production, between solar irradiance and cosmic rays. They match up perfectly. And this has been a measured phenomena. This is not hypothetical. This is actual data taken from a paper by Carcel et al. In 2002. It ends up, the correlation has been that they recognize that more clouds, more cosmic rays seem to result in more clouds and lower temperatures. And in fact, it's been measured that there's something like a 1.7% variation in low cloud formation between a solar maximum and minimum. So all these three things match up. And so the idea was there must be some kind of, the cosmic rays must have some kind of impact that result in the formation of more clouds. But there was all kinds of hypotheses put out as to why this might happen. And interestingly, a landmark paper was just published in the Proceedings of the Royal Society in October of 2006 by Svinsmark, and they have finally experimentally demonstrated how that happens. How cosmic rays excite electrons and result in forming more cloud nuclei. So we now, and this has been a problem with this hypothesis as a climate driver, is that they really didn't have a mechanism for it, or they had the mechanism, but they didn't have proof. Now they have proof. So let's look then at how this all fits together. The so what between my fish production, my phytoplankton, the clouds, the upwelling, and cosmic rays. See how it all impacts climate. So here's the idea. We have our solar system continually being bombarded by cosmic rays. Cosmic rays enhance cloud production on the Earth. The more clouds that you have results in less solar energy getting through to the Earth's surface and an overall cooling. Counteracting all that is the solar sunspot cycle. During the peak of a sunspot cycle, we end up with more solar energy, more solar wind, which deflects more cosmic rays. More cosmic rays deflected, we end up with fewer clouds. During a trough of a sunspot cycle, we end up with a lesser amount of solar wind, more cosmic rays get through, resulting in more cloud formation and overall cooler conditions, resulting in this graph that we see right here. So this is a smoking gun to explain what's happening. And in fact, the cosmic ray intensity varies by something like 15% across the sunspot cycle, which causes that 1.7% variation in cloud formation. Now, the interesting thing is, that's an 11-year sunspot cycle. As we ramp up to larger sunspot cycles, here's the Gleisberg cycle, the Seuss cycle, and so on, that it varies by a factor of 3 to 4. So we end up with a massive change in the percentage, the amount of cloud formation when you move up to these longer solar cycles. So they can have a profound impact upon climate at that point, not just relatively minor impacts. So here is the model which I think controls what we see. But before I do that, I want to show another interesting correlation. There's a paper by Hamid and Lee in 2003 at the American Geophysical Union. They looked at looking at the sunspot cycle, and they correlated with the center of formation or center of action, the place anyway where the Aleutian Low and the North Pacific High form every year. These are annual things that they disappear. The North Pacific High largely disappears in the wintertime. The Aleutian Low largely disappears in the summer. So they form every year. But where they start to form varies every year. What they found was there was an interesting correlation between the center of formation of the North Pacific High and the Aleutian Low and the sunspot cycle. And this can start to have an impact, because you think about, well, the North Pacific High controls upwelling, which my phytoplankton love. So if you have the North Pacific High just sitting in the very right spot, in the sweet spot, so to speak, you'll end up with enhanced upwelling and more of my diatoms. And as it moves around, it may move at a different part of the sunspot cycle to a center of formation which is not so nice, and we have less upwelling. And so this is what I think we're seeing. First of all, what we have is the sunspot cycle celestial modulation, which I described to you, looking at this cosmic ray flux and the sun changing over time. That has a big impact upon cloud formation on the planet as a whole. This in turn has an impact on something called planetary waves. Now, this is a fancy term. These are large-scale movements of atmosphere all around the planet, and the best example I can think of is the jet stream. Is a major thing which migrates, and at least on our Weather Channel here, I look at it every night and they're always showing, here's a jet stream, and this is why it's crappy here today, or this is why it's going to be nice today. And so this has a big impact upon this, what's happening with the Aleutian Low and the North Pacific High. So this has the correlation right here. Impacts the center of formation of the North Pacific High and the Aleutian Low, which are moving by up to 700 kilometers across the sunspot cycle. So think about what's happening here as we move up to Gleisberg cycles, when you start to enhance the impact by 3 to 4. So this is an enormous impact upon upwelling in this region. And this enhanced upwelling then is what we're seeing with our nutrients and our diatom production. So that's the climatic link between the proxy records that we see in Effingham Inlet and what's happening in the bigger global picture. The next thing I wanted to show you is that I mentioned with these Gleisberg cycles, they record intervals in here between high sun intervals when you have a peak solar production and intervals when it's lesser. And so here's, again, I showed you this diagram. Here's a high sun activity 4,400 years ago. Here's a low sun. Here's a higher sun interval again. I want to show you exactly what happened right at this point, and we'll look at it actually visually. And this is a nice thing about this sort of a time series analysis. You can actually lay the core down beside it and say, oh, what was going on here? Why does this cycle show up? And here's what happens. This is a 62-year climate record right here from 4,400 years ago, year by year by year. And the question would be, so what? What's the big deal about this? The big deal about this is everybody always talks about, when they talk about climate change and so on, well, climate's going to change suddenly, more suddenly than it ever changed before and so on. Well, you know what? Climate can change very suddenly and it can change very profoundly. And here's an example of that right here. Here are these thick layers right here, year by year by year, and everybody in the room could recognize then these are thicker, lighter layers. These are enhanced upwelling. Okay, this is the high sun interval right up here, when that sort of a light area right here. But look at this record, right at this point right here, suddenly we moved from a high sun part of a Gleisberg cycle to a low sun one, and almost over the point of one season, we changed to a different climate regime here. We see these darker, thinner layers. The diatom production is greatly reduced now, and now it's a lot of these darker, muddy layers from enhanced rain. The Aleutian Low is starting to dominate at this point, as opposed to the upwelling that was going on with the North Pacific High. And this occurred like that. Okay, so this is massive climate regime shift going on almost instantaneously. So it's ludicrous, the idea that climate can change on all scales. It can change slowly, it can change dramatically, such as we change around here. It can be colder or wetter. The records that we see here show how dramatically fast that change can be. Now just move to the north for just a couple of slides here to show what's happening up in the more continental regime. Okay, this is Belize Inlet, and this is a line right here. All these colors right here basically are showing changes in temperature, oxygen, and salinity that we measure with probes that we stick in to give us water property data. And so this is this long red line. Then this over here is another little inlet, which is blue, which basically you can see changes in temperature, oxygen, and so on. The main point I want to show here is that on top of in this inlet up here, the water doesn't have a very high salinity. This is a low salinity wedge around here. It's very fresh. The same thing up here, very fresh water, and it's more saline down below. And what's happening here is it's difficult for water to become exchanged through this place called the Natwatko Rapids. And the waters here is probably one of the highest tidal flows in the world at 8 meters per second. You'd be swept away if you were put in this water right here. This just shows the standing wave as the tide is turning in this particular place right here. So exchange is very, very difficult. And as a result, this place is not greatly influenced by the open ocean like we saw down in the south at Effingham Inlet. It's controlled largely by estuarine flow, the amount of rainfall that's coming into this area from streams or from other sources. So this is what we're seeing, although you do get a little whiff of some temperature change coming into the place. But we see the same pattern. up here. The high sun activity, the low sun, high sun, low sun, all responding not so much to upwelling this time, but it's responding to changes in rainfall. As the Aleutian low, which dumps lots of water around here, moves in, dumps water in this place, and then the North Pacific high so this is when you have North Pacific high, this is Aleutian low. So this is low rainfall, high rainfall, low rainfall, high rainfall. So it's not upwelling, but it's the same sort of phenomena. So it's a completely different oceanographic regime, but exactly the same sort of pattern going on. And what I think this is analogous to is like the little ice age in northern Europe. So here's something called the Maunder minimum. This is a time when sunspot cycles largely disappeared from that part of Europe, or basically from the world. Then they start to reappear again. So here's a sunspot cycle getting longer and longer and longer, a Gleisberg cycle it's piggybacked on top of that, and another one, and here we are up to present time. So we've gone from this sort of a cold condition, low sun conditions, up to much warmer conditions as we have at the present time. So it's the same sort of cycles and trends that are going on. Okay, here's Bruegel's Hunters in the Snow. So a picture from northern Europe. And so this is sorts of conditions that you do not see there at the present time, as existed during the Maunder minimum when there was hardly any sunspot activity and lots of cosmic rays getting in, forming lots of clouds. And it's interesting, if you look at practically any painting that's taken from that, or that was done during that interval, they always tend to have this sort of a hazy, cloudy sort of look to them, which reflects the sort of enhanced clouds conditions that existed, which resulted in the overall cooler type conditions. Now, the final thing that I'll talk about right here is we looked at a little ice age record actually from our core records up at Belize Inlet. So I'm not going to bore you. There's a way that we can look at the distribution of fossils in particular samples that live at the present time. So you go all different conditions, low oxygen, high oxygen, warm, cooler, whatever, and then we can correlate them to tell us about what the conditions are that exist at that present time. So this is a diagram which shows this. Here's the more interesting bit right here, is that we can actually then look at these different species that live around here, and you can see that in a very short freeze core that we took from Belize Inlet, that there was a radical change in this place. So there was some of these species were very abundant deeper in the core, then we changed to a totally different set. And using this thing called the transfer function, we can ascribe oxygen values and temperatures to these distribution of these fossils. And what we saw, the interesting thing is that at a point right here, and I think I'll move to another slide to show that, is that here is the transfer function. This is dated from about 1000 AD up to the present time in here. Up until about 1500 AD, oxygen levels in Belize Inlet were very low. Then almost instantly, they moved up to much, much higher levels. The same thing with temperature. Temperature was higher, then almost instantly around 1500, we moved to a lower temperature, which stayed all through the 1800s until the latter part of the 1800s, when it gradually, the temperature started to drop off and oxygen started to drop off as well, which matches up beautifully with the Little Ice Age. So I think what we're seeing here is another one of these Gleisberg cycle shifts that we're looking at. And here's just a little model to show how this happened, is that Belize Inlet, during the time when oxygen levels were low, basically it rained a lot in this area. So enhanced rainfall, which resulted in a very thick wedge of fresh water going across that very narrow little Waco Rapids out here. Water couldn't get in from the open ocean at all. And it resulted in this water in here becoming very stagnant. Then, as we moved on later, Belize Inlet, as we moved, the North Pacific High began to dominate in that area. It resulted in lower salinity water leaving, but it's a thinner wedge, and some water could actually get in, and oxygen levels start to go up again. And so it can happen very, very quickly. It doesn't take much. If you add a lot of water into this very narrow little inlet up there, it can result in a serious restriction of the amount of exchange going on and almost instantaneous development of anoxia. So this is our Little Ice Age record that we see in this region as well, which is controlled by, again, these movements in the North Pacific High and Aleutian Low. It's not upwelling. We're looking at changes in actual rainfall at this stage. So finally then, the conclusion that we've drawn from this research carried out over several years here, that basically we see very conclusive, I'd think, evidence of natural cyclic phenomena, which we think is driven by these celestial variation, which has an impact of the solar forcing basically being modulated by cosmic ray flux, which seems to be a prime driver of not only climate in the Northeast Pacific, but also has a profound influence upon biological processes as well. And that is it.